So, in this video, I address the topic of waves and uh, motion. So, when we talk about waves, you can think about sound, you can think about light, and you can think about water waves. So, we'll start by defining what this wave is. So, as I said, when we talk about waves, we have a number of things that we usually focus on: sound, light, water, radio, seismic waves, and the like. Now, really, when we talk about a wave, we are talking about a means of transferring energy from one place to another. So actually sometimes without transferring matter. So that's what we mean by a wave. So we are focusing on that transfer of energy. So we transfer energy by a means of a wave. What we have here is kind of a radio wave. So we can see that energy is being transferred from this source going outwards. So the energy is moving the direction of the arrow. Now, when we talk about waves, we can classify waves in two forms. We have mechanical wave. So among the mechanical wave, we have two types of them. So we have a transverse waves and longitudinal waves, and we'll see what that means. Then we have another wave form that we call electromagnetic waves. So actually, this is the wave that deals with light. Now, this electromagnetic wave is a transverse wave. So we don't have longitudinal as an electromagnetic wave. Now, let's look at these two types of waves: mechanical versus electromagnetic wave. Now, mechanical waves, some examples are water waves, waves on a rope, like a battle rope, sound. So the important fact about mechanical waves is that they must have a substance to travel through. So they must have a medium. So a medium can be water medium or air medium or glass. So here examples are air, water, or glass. That is medium. So these mechanical waves cannot travel in vacuum. They always need medium. And here for mechanical waves, we have vibrations that pass from one molecule to another. So if we start our wave here, these vibrations are passing from one molecule to another, one molecule to another, as the wave is moving in a specific direction. So important information about mechanical wave is that it must have a medium. Now, electromagnetic waves, so examples are radio, X-rays, and light. So the fascinating thing about electromagnetic wave is that it does not need a substance to travel through. So you don't need a medium for electromagnetic wave. Actually, it can travel through a medium, but you don't need it. Which means this wave can travel in a vacuum. So like light, we can have light in space, which is practically a vacuum. Electromagnetic wave has a specific speed. So the speed of electromagnetic wave is 3 times 10 to the power 8 meters per second. So this is something we talked about in class. Now we have what we call traveling waves. These are usually waves that travel from one place to another. An example is that waves on a rope. You can see initially the wave is at this point. As you are vibrating the rope, you can see the wave has moved to this point, has moved to this point, has moved to this point. So the wave is traveling from one point to another. That type of wave is called traveling wave. So examples are the waves on a rope, the waves on water, compression or compression waves on a spring. So all those are traveling waves because they can travel from one place to another. Now, if you look at a spring, so we say a spring as a wave. When you compress a spring and maybe release one side, the spring will be moving forward and backward. So the spring will be moving like this, like vibrating. As it is vibrating, at one point it is compressing, so we say it has a compression. At another point it is elongating, so getting a little bit longer than the compression side. So the elongation part is known as a rarefaction. So a spring has the compression part, which we call compression, and the elongation part, which we call rarefaction. So if we look at this spring, each compression and rarefaction will give you a wave. So like a single wave. So how many compressions and how many rarefactions you have will give you the number of waves you have in that spring. Now, just to introduce you to some important information of a wave, this is something that we are going to talk later, so maybe I should not waste much time on it here. So when you talk about a wave, you also need to think about the direction the wave is taking. So this spring, we compressed it and released one side. So the spring is compressing and expanding, compressing and expanding. But in general, it is moving in this direction. So when you talk about a wave, you also need to talk about direction of a wave. And we will talk about wavelength um, in terms of waves. So just take note of this length here. Now, when we talk about waves, um, we have two types of waves. This is depending on how they travel. So we have longitudinal wave or longitudinal wave and transverse wave. So longitudinal wave usually has these what we call compressions and rarefactures. So it has compressions and rarefactions. So that is the compressed part and the elongated part. While transverse waves, they move up and down, or they can move sideways or up and down. So can move sideways or up and down. So you can see this wave here is moving up and down. You can see the direction that is being given. While here the longitudinal, you can see that it is moving forward and backward, making compressions and rarefactures. So let's look at these transverse waves. Normally, transverse waves they move perpendicular to the direction in which the wave is traveling. So let's suppose the wave is traveling going this way. So this is the direction of the wave. A transverse wave will be moving this way. Up, down, up, down, up, down, up, down. So the wave is moving up and down while the direction is forward. So that type of wave is known as transverse wave because the direction of vibration is perpendicular to the direction in which the wave travels. Then we have longitudinal wave. Now this wave, both the wave and the vibrations are in the same direction. So here, a wave where the direction of vibration is parallel to the direction in which the wave travels. So an example is sound waves, waves that have rarefactures and compression. So they will take the same direction as the vibrations. So if you look at this example of wave, you can see that it is vibrating forward, backward. But as it is vibrating, the direction of vibration is the same as the direction of the wave. So you have the compressions and rarefactures, but these compressions and rarefactures are moving from the left here to the right. So that is a longitudinal wave. So I think I already talked about the transverse wave as a wave that moves perpendicular to the vibrations. Now, examples of these longitudinal waves are light waves, then we have radio waves, we have waves on a rope. So if you hold a rope this side here and the rope is moving like this, you are vibrating the rope, you can see that this type of wave is a transverse wave because this is actually the direction of the wave and this is the direction of the vibrations. Water waves are the same thing. So we have these water ripples. You can see that they move, they vibrate up and down, but the water is going downward or the water is going outward from the source of the vibration. So if we look at some examples of longitudinal waves, are the sound waves in a solid, liquid, or gas. So sound in air is an example of longitudinal wave. We talk about a spring, compression of a spring is a longitudinal wave. And the waves from the earthquakes, the seismic waves, are also an example of longitudinal waves. Now, when you talk about a wave, there are some important points that we need to take note. Usually, a wave is like a cycle. So if I start from here, from this point, and move to this point, this is half cycle. Then I can cycle back to where I started. So this is a full cycle. So each full cycle is a wave. Now, you can take this cycle and draw it this way. Say, this is my half cycle. Now, instead of going this way, I can say the other cycle, let me draw it the other way. So I have a full cycle here, but you can see that this full cycle is a wave. So what we call a sine wave. This is what we are saying here. We are starting from here to get to a half cycle. Now, instead of going this way to get a full cycle, we decide that we need to go this way to give us a full cycle. So from this point here to this point here is one cycle. So each cycle of a wave is known as the wavelength. So the length from here to here, so we can draw a line here, is called wave length. That is the length of one cycle of a wave. So generally, the way we define a wavelength is that it is a distance from one point on the wave to the corresponding point on the next cycle. So if we take this point here, we need to go to the other cycle and find the corresponding point, the point which is exactly the same with the other point from a wave. And you can say, now this is my wavelength. Distance from one point on a wave to another point on the next wave, but to another corresponding point on the next wave. I can start from here. If I start from here, I'll have to move this one to a corresponding point, which is this one. So that becomes my wavelength, because this point A is kind of similar to point B, only that they are from two waves, which are or from two adjacent waves. So what we are saying is the distance between two adjacent points on adjacent waves is called wavelength. Now, when we also talk about waves, there is another term that we call frequency. Let me just go back to wavelength. So another term that we call frequency of a wave. So frequency by definition is how often things happen. So for a wave, frequency is a measure of the number of oscillations. So oscillations are like vibrations or cycles. So an oscillation is a cycle. So frequency is a measure of the number of cycles or oscillations of a wave per second. So let's say we have time here. So time from here to here is 1 second. Now I will say, okay, let me check how many waves am I going to have within that 1 second. So I'll start from here. So I'll say, all right, how many waves do I have within 1 second? And when we say how many waves, I mean how many cycles do I have within 1 second. So the first cycle starts from here and ends here. So that is one cycle. The second cycle starts from here and ends here. That's another cycle. The third cycle starts from here and ends here. Then the fourth cycle starts from here, but then it doesn't finish. So the cycle keeps on and ends here. So we can say for this wave, we have 1, 2, 3 cycles, maybe 3 and 2/3. So we have 3 and 2/3 cycles per second. So that is what we call frequency. The number of cycles per 1 second. The number of waves or oscillations per 1 second is called frequency of a wave. Now, apart from frequency, so I'm going to erase this part. We have what we call a periodic time of a wave. So a period is just time taken. So a period is time taken All right, so let me get time taken for one complete cycle. So if I draw this normal of a wave, so I'll have my cycle starting from here, making half cycle here, full cycle. So the time it takes for one wavelength, the time from here to here is called periodic time. So periodic time is given as T. So this is a wavelength, and the time for one wavelength, the time for one wavelength is called periodic time, which is T. So time for one cycle of a wave. So if I do this, if I start from here and then start counting, the time I get here, I count how many seconds. Usually it is maybe millisecond or a nanosecond for of time for just one period. Now, there are important symbols when talking about a wave. Frequency is given as F, and the unit is hertz. In short, it is just Hz. So a hertz is cycles per second, like how many cycles per second of time. So here the wavelength has a symbol we call lambda. It's a Greek term. The unit we use meters, and the symbol for this unit is m. Then a wave has velocity. Usually the velocity is given the symbol v, but the velocity of light has the symbol c. So v is just any velocity of a wave, but c is the velocity of light. And so as we said, this is the velocity of light, c. So it's given in meters per second. So meters per second here, meters per second. Then we have time. Time of a wave is given by the capital letter or small letter t. That is the symbol for time, and actually it's given in seconds or s. So these are important units of a wave, important symbols and units of waves. So make sure that you understand them, you know them. So there are important relationships between waves and velocity. So the velocity of a wave, and this is c, is the velocity of light. So the velocity of a wave, including the velocity of light, is given by frequency times wave length. So wavelength is lambda, frequency is f. So this is the wavelength of light. This is the velocity of light here. This is just velocity of any wave. So the velocity of any wave is given as v. But now when it becomes light, then the velocity becomes c. So take note of this relationship, this equation for waves. Now, important terms about a wave, some of the things that we really discussed. So you look at two positions, two adjacent positions, and say this is wavelength. Now, each wave has what we call a crest. So a crest is like the highest points of the wave. The top of the hump. So you can see we have a hump here, and this point here is the crest. So this is a crest, and this is also a crest. Now, the lowest point of a wave is known as a trough. So you can see here we have a trough and we have a trough. Now, so this one I'll just say highest point of a wave. This one is lowest point of a wave. Now, the distance, this distance here from the center of the wave to the highest point, or from the center of the wave to the lowest point, this distance is known as amplitude. So this distance and this distance are called amplitude. So that's the distance from the center of the wave to the highest point or to the lowest point. So I can say distance from, let me give myself space here. So distance from the center of the wave to crest or trough, that is called an amplitude of a wave. So as I indicated, a wave has a cycle. So you can see a cycle, really the length of one cycle is called the wavelength. And here you can see that the wave is vibrating up and down. And as the wave is going this way, it moves at a specific velocity. If it's a light wave, it moves at the speed of light. Now, let's look at properties of waves. So the first property that we are going to look at is called reflection. So a wave has a property called reflection. So really, reflection is the bouncing of a wave off an object. So if you have an object here and you have a light that is hitting that object, then that light will bounce and it will be reflected. Now, normally when presenting waves, we use what we call ray diagrams. So I'll show you what a ray diagram is. So let me just get rid of this one. So if you talk about water wave, so let's take an example of water wave and think about the ripples. So this is the source. Like if you drop a rock in water, that rock is going to produce waves. And the waves will have higher points, which are crests. So the wave will be moving, will be making lines. So the wave will be making these vertical lines. But then the wave will be moving outwards while making those vertical lines. So what we are saying is, when drawing a wave, these lines that we have here are the waves we are talking about. This line showing the direction of a wave. So the line showing the direction of a wave is called a ray. So usually a wave is written, a ray is a line that is usually perpendicular to the actual wave. So this line here is a ray, but these lines are waves. So each wave, as it is moving, it has a ray, because the ray gives the direction of a wave. So you can see here, these are waves. Oh, hard to see. So these are waves. But this line here is a ray, because it gives us the direction of the wave. So when drawing ray diagrams, we ignore the wave lines. We just draw the rays themselves. So you see what it means. So reflection. What is this reflection of a wave? Now, let's say we have a light source here. We have a light source. So I'll just call it source. This light source produces light, the light that we call an incident ray. So an incident ray is the light that strikes a certain surface. So this is the light that strikes a certain surface. So you can see here, this light is moving downward to strike this surface down here. So that is the incident ray. Then the reflected ray is the light that leaves the surface. So you can see that the incident ray will bounce to become a reflected ray. So that's what is called reflection of light. Now, when thinking about reflection, you also think about the angle. So we have, this is known as psi. So we have angle of incident, psi I, and then we have angle of reflection, psi R. According to the law of reflection, these two angles are equal. So the angle of reflection is equal to the angle, the angle of, I'll say this. So the angle of incidence is equal to the angle of reflection, which means this angle here is equal to this angle. What does this mean? If you want to make a wide reflection, let's suppose you have a flashlight and you want to make a wide reflection, it means you need to increase the angle of the incident. If you want to make a less wide reflection, you need to decrease the angle of incidence. So if we look at this diagram, let me just clear everything. So if we look at this diagram, if you when drawing a reflection diagram, always you need to have this normal, because this normal is the one that gives you an idea about the angles that you are going to have. So we have a normal line, we have a normal line here, we have an incident ray. So this is the ray. You can see the direction. So the incident ray, the direction points to the surface. The reflected ray, the direction points away from the surface. And then we have the two angles, the incident angle here and the reflection angle over there, and those two angles are equal. Maybe how is reflection important? Like let's look about a real life situation. How is reflection important? Yeah, reflection is very important. If you are seeing your face in the mirror, that is reflection. If you are seeing things on a microscope, yeah, that is also reflection. So understanding reflection is very important, and the scientists have used reflection to check things. All right, so I think I will stop here on this video and do a next video to continue on this topic.